Okay, so by the time you see this video, you would have seen or learned somehow about polar coordinates on their own and rectangular coordinates on their own. And you could convert between the two one way or another. And then you would have also seen how to do area calculations with integrals in polar coordinates. All right, but I wanted to make a video that ties it all together with a little bit of everything. So I have this one problem that I think I can involve a little bit of everything that we've seen in one place. Okay, so of course it's up to you what you want to do, but what you might try is to try working this problem on your own, and then if you want to, you can resume the video and see the answer that I get to check your work. Okay. All right, so the question is, can you calculate the area contained by r is cosecant theta, r is 4 secant theta, those obviously in polar coordinates, and theta is equal to pi over 3. Okay, so there's our question. I want to do this in two different ways. All right, one, because this is a summary video, I wanted to show you a little bit of everything that we've seen. But two, I think that it's good to learn some flexibility in math. And you learn some math, you can learn all these different tools, and they're all available to you to use correctly. All right? And not everybody's going to do any given problem the same way. So I think you should learn some flexibility with what you know. So I'm going to do this in rectangular coordinates, and then I'll do it again in polar coordinates. And you'll see some flexibility in how I think about it, and you'll get to see a little bit of everything that we learned about polar coordinates. Okay, so my first method, I'm going to use rectangular coordinates. R is cosecant of theta converts to y is equal to 1, and that would be this horizontal line that goes through 1 on the y-axis, where my graph here is the rectangular graph, x and y. R is 4 secant theta converts to x is equal to 4, and that's going to be a vertical line at 4 on the x-axis. And that last thing that they gave us was theta is pi over 3, so that means that we have a line going through the origin at 60 degrees to the positive x-axis. Okay, now I want to find the area of this triangle. That's what the question amounts to. It says, can you find the area contained between x is 4, y is 1, and theta is 60 degrees. It's the triangle that you see. I located this point, and I said this point is right 4, and it's up 4 root 3. And the way I calculated that is that I see that, well, there's that shaded triangle that I'm trying to find the area of, but there's also this larger triangle. See this triangle that I'm outlining here? And that's 60, 30, and 90. And this side is 4, right? So you could use tangent if you want to. You could use the proportions of the 30, 60, 90 triangle. But for this larger triangle, the base there, the side adjacent to the 60-degree angle, is 4, and that will make this side, the side opposite the 60-degree angle, 4 root 3. Okay, now that's really the information I need to get started then, to find the area of this triangle. Let's resketch this. So I'm going to take that little triangle out, and at this point I'm going to lose scale. All right, I'm going to pick this up, I'm going to put it over here. What's this angle right there, in case we need to know it? Isn't it also 60? Yeah, so this is horizontal to the x-axis. That's inclined at 60 degrees to it. Well, that means that this angle right here is also 60 degrees. Okay, so we got a 60-degree angle there, and then that's going to be 90. And if you want that one, it's 30. Okay, what's this side? So if I take this triangle and I put it over here, well, so this entire distance was 4 root 3, but then what's this distance right here? This vertical distance, that's 1. So isn't the height of that triangle going to be 4 root 3 take away 1? All right. 4 root 3 take away 1. what about this side there adjacent to that 60-degree angle? Let's call it, I don't know, let's call it A, all right? So I will say tangent of 60 degrees, so tangent is opposite over adjacent, is 4 root 3 minus 1 divided by A, right? That's how you use tangent. I know the angle, I know the opposite side, and I want to find the adjacent side so that I can find the area, because that's what I'm after. And tangent of 60 degrees is root 3, so that makes A equal to 4 root 3 minus 1 over root 3. Okay? All right, let's reduce that a little bit. Let's say if I divide everything here by root 3, I'll get 4, because that's 4 root 3 divided by root 3, minus 1 over root 3. But I'll go ahead, I'll give you the rationalized form of that, root 3 over 3. Okay, so that's that base right there. Now, all right, we have all the information we need. The area of this triangle will be 1/2 its base times its height. And now I know both of those. Base I just found, the height I found as I drew this picture. Okay, so all right, let's do that over here. Area 1/2 base, okay, so that's 4 minus root 3 over 3 times height, 4 root 3 minus 1. Okay. So, if we, say, use FOIL multiplication on this, ignoring the 1/2, and if we combine some like terms and add some fractions and do a lot of that stuff you learn in algebra, then this is what you'll get. You'll get 1/2 49 root 3 minus 24 over 3. Okay. All right. And if we do one last thing, multiplying these fractions together, we'll get our final answer in exact form. Let's say 49 root 3 minus 24. That's 1 times that numerator, and then 2 times 3, so that's going to be 6. All right, so there's your number. That's the exact form of it anyway. Now, I noticed that when I made this, I tried to be very exact about it. I actually got my ruler and my protractor, and I measured the angle, and I measured 4 centimeters and 1 centimeter. So I wanted to have a scale. I wanted this to be about measurement. I'll let you know if you can use tools and confirm your math. I think that that's a good thing. So I did measure it correctly. And I get this exact answer, but let me round it. So if we use our calculator, 49 root 3 minus 24, divide by 6, we'll get 10.145, and I've got units to that. I know most of the problems we've done, we may have been measuring area, but we didn't. We just gave a number. We didn't actually treat it like a measurement. So, but this would be square centimeters, right? If the distances on my graph were in centimeters, if that's what the lengths were on the axes, well, this would be area. That would make it square centimeters. Okay. All right. So I think it'd be nice, you know, you're in calculus too, that you can work with exact numbers, right? I mean, none of these are rounded. Those are all exact. And even here, area is 1/2 base times height. All that's exact. If I FOIL all this and combine like terms and add the fractions together, that's all exact. That's the exact answer. It's got perfect precision. Then we might round it to however many decimal places would be appropriate. All right. Okay, with me measuring with this very crude ruler, then giving the answer to the 1,000th place might be a little bit much, but that's what it is to 3 decimal places. If you want to check your work, all right? Okay, so that's how you do it in rectangular coordinates, okay? Let's talk about using polar coordinates. So that'll be my second method. So I went ahead, I resketched it, and you have the same picture here. The scale is still in centimeters. This is 4 centimeters over, 1 centimeter over, but I left everything in polar coordinates. R is 4 secant theta, R is cosecant theta. Here's theta is pi over 3. And right here where this triangle begins, okay, so we want the area of this shaded triangle right there. That was the original question. There's this point where 4 secant theta and cosecant theta, there's a point where they intersect, okay? And I went ahead and put that for reference. Let's say that's angle A. All right, here would be the setup. This would do it. Like what you see here, this integral, that would work in polar coordinates. So the bounds of my integral are angle A, which I haven't told you anything about it yet besides to include it in the picture, over to pi over 3 of 1/2 16 secant squared, okay, minus cosecant squared d theta. I want you to notice some things about this. Why put it like that? Well, between angle A, which I haven't told you anything about yet, and pi over 3, is it true that in a radial fashion, the space is between this curve and that curve? Or if you don't want to call them curves, this graph and that graph? Isn't it true that if I have my angle here and I tilt it out all through this region in a radial fashion, 4 secant theta and cosecant theta contain the area, all right? And 4 secant theta is radially further out, and cosecant theta is radially further in, but the space is between those two things. Now, when we have that situation, if, you know, this one is radially further out than that one, and the area is between them from angle A to pi over 3, then our integral would be correct. All right, it's set up the right way. Okay, the triangle is, in fact, radially between 4 secant theta and cosecant theta from angle A over to pi over 3. Okay, otherwise, this is 1/2 r2 squared minus r1 squared d theta. All right, now, obviously, to do this, we're going to need to know more information about that angle. Okay, but I have a trick that I'll show you in a minute for getting what I need out of that. Now, let's say for now, we don't know what angle A is. Okay, do we at least know the antiderivative of 1/2 times 16 secant squared plus cosecant squared? Yeah, we know the antiderivative to that. Let's see. It is 16 times tangent, okay? Because the derivative of tangent is secant squared, plus cotangent, because the derivative of cotangent is negative cosecant squared. So that's actually pretty easy integral to do. Then I say from angle A to pi over 3. All right. So, okay, let's do the math with the upper bound right there. So I'll get this. Tangent of 60 degrees, tangent of pi over 3, turns out to be root 3. So I'll get square root of 3. And then cotangent of pi over 3, cotangent 60 degrees, is 1 over root 3. Okay? And that would be my math with my upper bound for my integral. Minus, okay, so 1/2 16, what? Oh, angle A. We didn't really find anything about angle A. Okay? Well, so I have a trick I'll show you in a minute, but let's look at it like this. Is it true, let's see, angle A is like this. This angle right here, right? Okay, in this triangle, right? See that triangle like so? Okay, what do you know about the triangle? Well, I happen to know this distance. What's this vertical distance? How far up did we say that was? It's 1. And what's this distance? Well, a minute ago, what did we say that distance was, that horizontal distance? That was 4. So I could do like this. I could say A is tangent inverse of, well, tangent of A would be 1 over 4, so tangent inverse of 1 over 4. All right. So I guess you could say, well, that's the angle, tangent inverse 1 over 4. I'll go ahead, I'll give you the angle in degrees. So tangent inverse 1 over 4. All right, see that? It's 14 degrees, slightly above 14 degrees. All right, I'm going to go ahead and put about 14.03. Now, I told you I like tools. I like to confirm math I do with a measurement, like in a laboratory if I can. Let's see what I made the trouble to draw this to scale. What's it say? So there is 10 degrees, 11, 12, 13. My protractor is like 13 and a half. Well, so my picture's not perfect, but well, I'm happy enough with it. All right. Okay, 14 degrees though, 14.03 to the 100th. Now, so let's see. That's what that angle is. And that's, I guess, what you could use here. But what if I wanted it exact? Like, I don't want to use some rounded form of that. So look at it like this. To do this part, I would have to say tangent of A. Where's angle A? It's right there. What's the tangent of that angle? 1 over 4. It's right in front. It's right there in the picture. Well, okay. Tangent A is 1 over 4, right? Okay. Now, what about cotangent of A next? Cotangent of A. So we're putting that lower bound in here and here. Tangent of angle A, 1 over 4. It's right in the picture. Cotangent of A. It's also right in the picture. See this angle, A right there? Well, it's cotangent. Cotangent is adjacent over opposite. It's 4. So, 4, like so. All right. So there, we worked the integral. We could have worked it without really even knowing that. Okay? If it makes you feel better, it's 14 or so degrees, but we don't even really need to know what it is in terms of a degree or radian measurement to do the math. It was in the picture the whole time. So anyway, what we'll do from here is, let's say I distribute to half, and I'll get, let's do like this, 8 root 3 plus, and let's call that root 3 over 3, so root 3 over 6. So that's what I'll get out of that one. And then here I got 4 and times a half, so that's -2. And then minus half times a 4 again, so that's also -2. Now, if at this point we do things such as combine like terms, the root 3 terms being like, get a common denominator with the fractions, and do all that stuff, then here's what we're going to get. 49 root 3 minus 24 over 6. Okay? It will take some algebra, but it's all algebra you've learned. If you need to talk about it, if you're not sure how to get from here to here, that's of course something that I'd be happy to talk about or make another video about. But I'll assume, it's a reasonable assumption that you know how to do it, unless you tell me otherwise. Now, that's the same thing we got here. Of course it's the same. The area is whatever it is, no matter how you find it. But all right, I drew this graph. It's in scale to centimeters, so I'll give you the same final answer. If you were to round it and include the units, 10.145 square centimeters. All right, this is a measurement. It does have units, and that's what they are in this case. All right, so hopefully you saw some flexibility. All right, for me to go through this and use each method to work the problem, I really have to know, like, what are polar coordinates and how do you think about them? How do you convert between polar and rectangular coordinates? And how do you measure area in polar coordinates, and so on? Those three things are connected together. Can you think of a third way to do it? I was like, I don't really think I've thought of the only ways that you can work this one. That's just what occurred to me when I was thinking about this earlier. So I'll leave it up to you. Can you think of, I'll just leave you with this challenge. Can you think of a third method? Okay, so part of learning math, I think, is to learn to be creative and do things your own way and not simply do what other people showed you to do step by step. So can you think of a third way to do it somehow with what you know? I'll just leave that open. If you can, I'd like to hear about it. If you can think of something really creative, I might make a video about it if it's something I think everybody would benefit from seeing. But I'll leave you with that challenge. Let me know how you do.